An introduction to organic chemistry. Organic compounds contain carbon and hydrogen. Sometimes we can have other nonmetals, such as oxygen, nitrogen, or sulfur in those compounds as well. But the key feature is the carbon atom, and carbon can form strong covalent bonds with itself in chains and rings. Carbon has the electron configuration 1s2, 2s2, 2p2. It will always form 4 covalent bonds. Let's look at the different bonds carbon can form. Single bond is a sigma bond. The hybridization is sp3, tetrahedral geometry. C2H6, for example, looks like this. There is free rotation around the carbons, and the bond angle, even though it doesn't look like it, is 109.5 because it's tetrahedral geometry, so it's not a flat molecule. Carbon-carbon double bonds have sigma and pi bonds. sp2 hybridization, trigonal geometry. If you have a double bond, there is no free rotation, which means these hydrogen will always be on the same side. The bond angle is 120 in a trigonal. And then you have carbon-carbon triple bond, sigma and 2 pi bonds. Hybridization is sp, it's a linear, so the bond angle is 180. Just like with double bonds, there's no free rotation. So C2H2 would be an example of that type of molecule. We're going to look at isomers, which are molecules with the same formula, but they're arranged differently. There's different types of isomers. First off, skeletal or structural isomers. Same formula, differ in the arrangement of the carbon atoms. C4H10. One way to draw C4H10 would look like this in a straight chain. So this is called a straight chain alkane. Another way to draw C4H10 would be in a branched chain like this, and then we could put the hydrogen on carbons. Carbon always forms 4 bonds, so we assume hydrogen is there even if it's not written because we know carbon always forms 4 bonds. Positional isomers differ in the location of a non-carbon group without changing the carbon skeleton. Bromobutanes, for example. Here's an example of a bromobutane. This one is called 1-bromobutane because the bromine is bonded to carbon 1. This isomer would be called 2-bromobutane because the bromine is bonded to carbon 2. So I didn't change the carbon skeleton, I just changed where the bromine was bonded. Functional isomers, change of one functional group to another. We'll look at functional groups in the next section. C2H6O, one way to draw that compound would be in an alcohol. This functional group, anytime you have an OH, is called an alcohol. I could also draw this molecule as an ether. The functional group with the oxygen between 2 carbons is called an ether. Geometric isomers differ in the geometric orientation of atoms. For example, C2H2Br2. One way to draw this molecule would be to have the bromine on the same side. If the bromine are on the same side, it's called a cis isomer. Since there's no free rotation around the carbons, the bromine will always be on the same side. I could also draw this isomer with the bromine on opposite sides, and this would be called a trans isomer because, again, the bromine would always be on opposite sides because there's no free rotation around the carbons. And then finally, optical isomers are non-superimposable mirror images. Only happens when carbon is bonded to 4 different things. For example, let's look at this molecule right here. This wedge means that bromine is coming towards you, and the dashes mean that iodine is going away from you. Because you have to think in a 3-dimensional space here, because the bond angle is 109.5. Let me draw the optical isomer of this molecule. It would look like this. So again, the Br is coming towards you, the I is going away from you. These are different molecules. They are non-superimposable, but they are mirror images. If I put a mirror right here, they would be mirror images, but they're not the same molecule. Those are called optical isomers. We're going to name organic compounds. We'll first look at alkanes. Alkanes have the general formula CnH2n plus 2. When we name organic compounds, we have to know the prefixes. Here, the prefixes from 1 through 10, indicating the number of carbons. So meth, eth, prop, bute, pent. Some of these sound familiar to you. Some are going to be a little different. Like the first 4, meth, eth, prop, and butes, are probably a little different than what you've heard in geometry class, for instance. But 5 through 10 should be very familiar. Alkanes mean we have single bonds. For example, C5H12 is called pentane. If I were to draw pentane, I would draw a straight chain carbon compound with 5 carbons. That would be pentane. I don't have to draw the hydrogen, but I know that carbon always forms 4 bonds, so there would be 3 hydrogen coming off the first carbon, 2 hydrogen coming off the second, 2 off the third, 2 off the fourth, and then 3 hydrogen coming off that last carbon. But we don't always have to draw the hydrogen when we draw organic molecules. Okay, so that's a straight chain. When we named branched chain alkanes, we're going to find the longest chain, and then we're going to indicate the position of substituent groups with the lowest possible numbers. Let me give you an example of a compound. First thing, I want to find the longest continuous chain. And I'm going to kind of circle it. The longest continuous chain is right here. That's the longest continuous chain. We have substituents right here and right here. Those substituents, it's a 1-carbon chain. They're called methyl groups. So we have 2 methyl groups that are called substituent groups coming off of the longest continuous chain. The longest continuous chain is 7, so we'll number that chain 1 through 7, like this. We're going to indicate where these substituents are. These substituents are on carbons 3 and 5. So here's how we would name this compound. 3, 5. We're going to say dimethyl, since both substituents are methyl groups. Di indicates that there are 2 of them. And then we're going to name the longest chain, which is 7. 7 is hep. And then the suffix is ane. So it's 3,5-dimethyl heptane. Here are some other substituent groups if they're bonded to the longest chain. And the prefixes. If you have more than one substituent group, we're going to use prefixes: di, tri, tetra, and penta. If a numbering choice occurs, we're going to number the chain so that the substituents are in the lowest possible positions. For example, let's say we have this compound right here. And again, I'm not drawing the hydrogen. We assume they're there because carbon always forms 4 bonds. The longest chain is 4, and we have a substituent here and here. We can either start numbering from left to right or from right to left. Well, if a numbering choice occurs, we want the substituents in the lowest possible numbers. So we're going to start carbon 1 over here, and we're going to number from right to left. So the substituents are called methyls. There's 2 methyls, and they're going to be on carbon 2. So we're going to say 2,2-dimethyl. So they get the lowest possible number, not 3,3, but 2,2, because we're numbering from right to left. And then the longest chain is 4. 4 is bute. So 2,2-dimethyl butane for this compound. If 2 or more substituents are present, we're going to list them alphabetically while ignoring the prefixes. So let's look at this example here. Longest chain is 7. We have a substituent here, which is called methyl, and a substituent here, which is a 2-carbon chain, that's called ethyl. Regardless of how we number, the substituents are going to be on carbons 3 and 5. So since these substituents will be on carbons 3 and 5, alphabetically ethyl comes first, so I want to start numbering from left to right, not right to left. And so ethyl comes first alphabetically, so we're going to say 3-ethyl, 5-methyl, indicate the substituents first, and then name the longest chain, which is 7, so that is heptane. So 3-ethyl, 5-methyl, heptane. So here's a summary for the branched chain alkanes as far as the rules that we follow. Cycloalkanes are rings. They have the general formula CnH2n. They are saturated. Nomenclature is cycloalkane. We're going to put the prefix in the middle. For example, cyclopentane, you see the cyclo. It's a ring structure. Pent means 5. And so we've got a 5-carbon ring structure. And since carbon always forms 4 bonds, each carbon has 2 hydrogen attached to it.